Okay, so the exams, I don't recall the average or anything. I think it was 70 something, yeah. I don't even remember the number of A's and B's. Do I have it? Let me see if I have it. I may not have done a summary here. It's been the whole weekend. Let's see. No, I don't think I have it. Okay, it's not on this computer. All right, so we can talk about the grades, later. In Canvas, I've already accounted for the 10-point bonus. If you had done that thing for me with the transcript earlier in the semester, it should be there. It should appear as a bonus. You'll see a column for a bonus. If I did not give you credit, that means I was not able to find the email that you were supposed to send to me that's supposed to have in the subject line the title of the section that you did, and then attached to it should have been the transcript. So if you did it and you sent it to me and I didn't find it, you need to talk to me, maybe after class. Okay? Yes?
And it hasn't affected a grade?
I'm sorry?
It hasn't affected a grade to the end, right? Like whatever.
It's factored in. It is counting it right now.
Oh, it is?
Yeah, but you know how you can just like mess with your grades? Just go in there and mess with your grades, see what you need on the, final. And the way that Canvas does the grades is somewhat confusing. So if you're concerned about anything, just go. We only have one more exam, right? Right? We have one more exam. So just go in there and just mess with that exam grade to see what your score would need to be in the class.
So it's already at the 10 points?
Yes, but it's... Again, the way that Canvas does it is, it doesn't look like it did until you put in that final exam grade. Okay? So like if I have a test student that I can run hundreds across everything, right? And when I do that, that student ends with 110 in the class. Okay? If I take that quiz out, they end with 100, which is the way that should work. So if we've had so many quizzes up to this point that another quiz or two that we have, that quiz grade should not fluctuate too much at this point. I mean, it might. It depends. If you get zeros on them both, it's gonna hurt. But it's not gonna be like drastic. So, okay. Exams are up here if anyone didn't get theirs. All right. Let's see. Jeremiah and Maxwell, right?
Yes.
There you go.
Thank you.
Okay. All right, we have to continue to move. All right, so we are going to pick up where we left off. This actually is not where we left off, though. I wanted to bring something to your attention. Remember, with the geometric series will always converge if the absolute value of r is less than 1. All right, we should be all comfortable with that by now. And in a lot of the problems that I did in the homework on video, you'd see that my goal was to try and make this thing in here look like a times r to the n minus 1, right? And sometimes making it look like n minus 1 required some hidden zeros and things like that. Keep in mind that there is an equivalent formula for a geometric series that uses a times r to the n instead of n minus 1. And the big difference between these two formulas is just where they start. Okay, this one starts at 1, right? So if I start at 1, when I plug 1 in here, I'm going to get a 0. So my first term should be a times r to the 0, right? Which is a. This formula does the exact same thing, but it starts at 0 instead of 1. And so if I start plugging values in, if n is 0, I get what? R to the 0, which is 1 times a. So I get a, the first one. And then the second one, I'm going to get a, r to what power? 1, right? And then plus AR squared. And that is the same series. So what I'm getting at is from here on out, anytime you see a geometric series, if it starts at n is 1, you want to make it look like that. But if it starts at n equals 0, you want to make it look like this. Okay? So two differences in the exponents. Understand? Okay. Now, also, when you're messing with geometric series, if you're asked whether or not a series converges or diverges, all right, let me look at a specific example. if I put up a series here, excuse me, n equals 1 to infinity of, let's say, 4 times 3 to the n plus 2 over 5 to the n minus 3. Let's say we did that right there. And you were asked, does this converge or diverge? Right? If you were asked that, then what would you do? Would you go and you have to make sure it looks like a geometric series, okay? Which it does, because you got your n is in the exponents. So would you actually have to go make it look like this to answer the question?
No.
You would not have to make it look like this. We all at this point would understand that this could eventually be written as 3 to the n minus 1 times 3 to something, right? And then this down here could be rewritten as 5 to the n minus 1 times 5 to the something. And this 3 to the something and 5 to the something, it's going to turn out to come out here as like an A. What's important is the things that are left to the n minus 1, which are those two things, right? And that would be a 3 over 5, right? 3/5. And the absolute value of 3/5 is less than 1. So if I were presented with this problem right here, okay, without all this in here, what I would say is it converges because r is equal to 3/5, which is less than 1. And I have answered the question, haven't I? It did not ask what it converged to. If it asked what it converged to, then I would have to go through the whole setup to figure out what A was so that I could use the formula A over 1 minus R, right, for the convergence formula. But if it's just asking converge or diverge, it's just recognition straight to here, done. Okay? Questions? Now, in the test, I did say if it converges, find the sum. I did say that on the test. So you did have to go all the way. I'm saying from here on out, a lot of these problems are going to be converge or diverge. All right? Anything else on that? I think that's good. I think I can move on. You know what? We'll do one example. All right. So look at the instructions. What are the instructions? Find the sum. That means right now it's either geometric or telescopic. Okay, some of y'all confused that on the test because I said, does it converge or diverge? If it converges, find the sum. Some of you like circled find the sum and you said like, oh, it's geometric. No, it's only geometric or telescopic if I tell you to find the sum. If I tell you to find the sum, that means it converges. Like it converges. I'm telling you that to begin with. So here, what would we do? How do you mean?
The exponent, n minus 1 needs to be in the numerator.
Okay, so I could rewrite this as a fraction, 1 over the square root of 2, all of this to the n minus 1. Couldn't I? I could not write that? I thought I heard no. Sorry. No. That I could do? Now, is this the right formula? Is this the right format that I need? Do I want n minus 1 up there? I do not want n minus 1 up there. Why? Because I'm starting at 0. Okay, so this is the slight little change we have to pay attention to now. So I really want this to be what instead of n minus 1? Just n, right? So to make that just n, I'm going to go and rewrite that as sum n equals 0 to infinity. And now, how about I write it this way? N and then like that. Isn't that the same thing? If I put these two together, you add the exponents, n add negative 1 is n minus 1. So now I have it to the n power, which is in the right format. Now what's a for us, though, in this? It's this part right here, right? That's a. This is a. So a negative exponent on a fraction means I can flip the fraction over. So this is really just root 2 times 1 over root 2 to the n. And now it's geometric, right? The new geometric with n starting at 0. And so this should add up to be a over 1 minus n. So a over 1, did I say n? I did say n. A over 1 minus r is what I meant to say. And that is because r is what here? 1 over root 2, which is less than 1. So we know it converges, right? Okay, and I'll just leave the rest to you. I just wanted you to see the difference between having it, having this problem, you could get tricked by saying, oh, it looks geometric, n minus 1 is what we've always been using. You now have to pay attention to that starting point on that index. Okay, now we will continue from where we were before the test. Right now, if somebody gives us a series, okay, going off this sheet that I've handed you, or that you have online, right now, if we want to figure out if a series converges or diverges, we have the nth term test, which is only a good test if when we take the limit we get something other than 0, then we know it diverges. Otherwise, the test fails. The next thing is the geometric series, which we, again, have conclusions for a geometric series. It all depends on R. And then how about below geometric? We haven't talked about p-series, have we? We have not done that. Integral, that we did do. So remember what the integral test said. It said that if we ever have a series, right? If we ever have some series, then, and we want to know if it converges or diverges, what we can do is we can change this series into some function of n. So a function over the real numbers. We can make sure that that function is continuous, that it's positive, and that it's decreasing. And then we take the integral. And if the integral converges, the series converges. If the integral diverges, the series diverges. So I think I did like one example of that. And now I'm ready to move on to the next thing, which actually we're going to go up and take care of p-series now. All right? So the question is this. Maybe we can come up with a general formula, a general idea here for this thing called a p-series. A p-series is any series that looks like this. Sum n equals 1 to infinity of 1 over n to the p. Now here p is like a variable, right? P could be different values. It could be 2, it could be a half, right? So p is the power, that's why we call it p, all right? So this is like a power series almost, like a reciprocal power series. The question is, when does this converge? When does this diverge? Okay? That's the question. Now what does the test say? The test says what? If this number up here is greater than 1, we are going to converge. And it says if this number here is less than or equal to 1, we're going to diverge. All right? So let me show you an example of that. Sum, so as an example of p-series, n equals 1 to infinity of 1 over n squared. Okay, does that converge or diverge? It converges. Why? Converges because it's a p-series, right? And it's a p-series with p equal to 2, right? Which is greater than 1. And the test says that if p is greater than 1, we converge, right? Okay, so let's try something else. What about sum n equals 1 to infinity of, how about n cubed over the square root of n? Does that series converge or diverge? Diverges. Okay, so first you have to see it's a p-series. Let's see. Let's check this out. Maybe converge, maybe diverge. Let's see. Sum n equals 1 to infinity. How can I rewrite this right here? So this bottom is same as n to the half, right? So if I do 3 minus a half, I get 5 halves? So this is same as n to the 5 halves. Is that a p-series with n being 5 halves? No, you have to be a p-series, has to be 1 over, right? 1 over. So I could rewrite this as sum n equals 1 to infinity of 1 over n to what power? Negative 5 halves, right? Now it looks like a p-series. This is a p-series with p being what? Negative 5 halves, which is less than 1. And what happens when your p is less than 1? According to this, it diverges, right? Hey, and what if p is 1? What if p is 1? What if that was a 1 right there? We're going to diverge, right? Do you recognize that series? What's that? We did that. That is the harmonic series. So the harmonic series, we already showed that that diverged, kind of. So the harmonic series is an example of a specific p-series where p is 1. But anytime p is less than 1, we have divergence. So this means diverges. Isn't that a pretty easy test to run? P-series, pretty simple. Just identify p, you're done. Okay, so why does the p-series work? Now I'm going to actually show you why it is. Okay, we could just take it on faith and we could move on, but this is a Cal 2 class, so where does this idea come from that if p is bigger than 1, we converge, and if p is less than or equal to 1, we diverge? So let's go back to this original question. Here it is. So we want to know if this converges or diverges, right? Let's act like we don't know the results of this table or this test sheet. So if I'm going to try and do that, what I'm going to do first is I'm going to create a function. And I'm going to call that function 1 over n to the p. All right? And I'm going to run the integral test on it. Okay, so I'm about to run the integral test. So the integral test says you have to look at this function and make sure it's continuous on the interval 1 to infinity. So is that function f of n equals 1 over n to the p continuous on the interval 1 to infinity? That's a question. Now, if the n is confusing you, what this really means is like x to some power, right? If you want to use x as your variable because this is a real number, you can use x. Is this always going to be defined on this interval? Yeah. I mean, as long as x isn't 0, you're in business, right? You can take a number and raise it to these powers. Whatever p is, that's defined. Okay, what's the next condition we need? We need to be continuous. What else do we need? We need to be positive. Is this always going to give you a positive number? Yes. Yes, because I'm plugging in a positive number for x. X, if it's positive, raised to any power is still positive, right? So is f of x positive greater than 0 on this interval? Yes. Yes, right? What's the next condition? Has to be decreasing, right? So is f decreasing on the interval 1 infinity? That's my little symbol for decreasing. Is it?
Yes.
How do you know? Number on the bottom is getting bigger. So how is it? That is a good argument, but how do we show it if it were a more complicated function? We take the derivative and make sure that we can show that that derivative would always be negative. So let's take the derivative of this function. What is the derivative of that function? So that function is really what? X to the negative p. If we bring that back up, and when you take derivative of that, what would you get? Negative p, x to the negative p minus 1, which is the same as negative p over x to the p plus 1. So all we did here was well, this was power rule, right? Negative p came out, and we subtracted 1. Then I took a negative out of this and dropped the whole thing down and got this. Okay, now is this always negative on that interval?
Yes, because the numerator is negative.
Well, could p be negative?
Could it? It's between 1 and infinity, not...
No, that's x. So don't confuse p and x, all right? So wait a minute. No, it's all right. It could p... So would you all agree right now that if p is greater than 0, let's say p is a positive number, right? Then this will be what? This numerator will be what? The numerator will be negative. And what about the denominator? Should be positive, right? Because we're taking a number that's on this interval, right? And we're plugging a power into it that's positive, which, well, this bottom should always be positive, right? Positive number raised to any power. So that's what we get, right? So what if p is negative? So if p is negative, right, less than 0, then what would happen? The top would be positive, and the bottom would be still positive, right? Because if that's a negative number, it doesn't matter. What if this whole thing on the bottom turns out to be negative? X to a negative number just means move it up top. So we still get positive. So, we have a problem here, don't we? We have something going on here. This says as long as p is what? Bigger than 0, we have decreasing, right? So we're going to have to look at what if p is not, if it's negative in a little while. Because this would mean it's increasing, right? You all follow me? Okay. So right now we have a condition. So long as p is bigger than 0, then we have this way to go, all right? All right, so let's continue here. What are we going to do now? All right, we've got all the conditions met. So long as p is greater than 0, we can do the following. So if p is greater than 0, then we can run the integral test, which means we want to do the integral from 1 to infinity of 1 over n to the p, x to the p dx. That's what we want to do, right? Integrate the function from 1 to infinity, see if we get convergence or divergence. So now we take an antiderivative. Remember, this is x to the negative p. So let's do an antiderivative of that. What's the antiderivative of that? What's the power going to be? X to the negative p plus 1, right? But what goes out front? We have to have something out front. 1 over negative p plus 1. Right? Look, if this was x to the negative 2, you'd be adding, right? Adding 1 and then... Do y'all agree that's the antiderivative? Okay. Also, we need to integrate this from where to where? 1 to infinity. Now, in previous section, this was called an improper integral. So this is where we do a limit, right? Wouldn't we? Because we don't have all the time in the world for this notation, I'm just going to be like asking you to remember that this infinity is really a limit. So when I go to plug this infinity in, I'm going to be treating it like a limit instead of infinity, right? Okay, so let's try this. This part gets a little bit tricky, all right? Equals. Okay, we're going to have two things. This one is what happens when I try and let that go to infinity, right? And this one is what I get when I plug in 1. So let's do the 1 first, because the 1 is easy. If we plug in 1 for p or x, if we plug in 1 for x, 1 raised to any power should be 1. Okay, so all we get is 1 over negative p plus 1, right? That's what would happen there. We plug in 1. Okay, what would happen if we plug in infinity? What's that? I can't understand what you're saying. Refract? What? Oh, sorry.
I only got it on the first time.
What the hell? Okay.
What's in that drink, man?
It's not strong enough. That's the problem. We're plugging infinity in for x. What happens? So if this gets big, right, and then we're raising it to a power, does that get big? Depends on the power, right? Because if this number up here turns out to be negative, then it's really 1 over it, isn't it? But if this up here is positive, then it's just infinity to a positive number. So we have to actually look at two different cases here. Do y'all see that? So this part into here, I'm not sure. So here's what I'm going to do. Now I'm going to break this down into two smaller subgroups. Okay, if P, let's say P, negative P plus 1 is greater than 0. So let's say that that power is a positive number, right? Then that, plugging infinity in, this thing blows up, doesn't it? And that means this side goes to infinity and this thing does what? Diverges, right? So if that power is greater than 0, then that integral from 1 to infinity of 1 over x to the p dx diverges. Yes? Do you all agree? Now, what is another way of saying that negative p plus 1 is greater than 0? Another way I could say that is p is less than 1, right? Just move this p to the other side. 1 is bigger than p is the same as saying p is less than 1. So if p is less than 1, I've got divergence. Yeah? Yes? Okay. What about if negative p plus 1 is greater than, not greater, less than 0 this time? So now let's say that that power up there is negative. Let's say negative 1, right? Then when you plug a huge number in, it's going to be 1 over that huge number. That should all go where? To 0. That should go to 0. So this whole thing right here is gone, which leaves you with this, right? Which leaves you, and this is a finite number. Agreed? This is a finite number. So what would that mean? That means that integral does what? Converges, right? Now, do we know what it converges to? Be careful. Do we know what the series converges to? We know the integral converges to a number, right? But this number has nothing to do with the series. It just tells us that we have convergence. If the integral converges, the series converges, all right? So what's another way of saying this statement right here? P must be greater than 1, right? Right? P must be greater than 1. And what if P is 1? What if P was 1? How would we know it diverges? Okay, so if P is 1, it's harmonic. So we knew it diverged, but I kind of convinced you by showing you something. It wasn't as convincing as we could be right here. If we just replace this with a 1, right? This formula doesn't work anymore. Do y'all agree that doesn't work? Because this isn't defined. But that's okay, because what's the antiderivative of 1 over x? Natural log of x. And now if you do this and this, natural log of infinity is infinity, it diverges. Okay? So what we have here is that we can change this right here for divergence. We can actually make that strict inequality, or not strict, we can include the point 1. I'm doing this very loosely just because you don't have to prove this on your own. I'm just showing you where it comes from. The P-series simple check we're going to do comes from an integral test. That integral test creates the P-series test. All right? Let's see. What have we not considered? What have we not considered? Okay. All of this that we did was based upon one condition. What was the condition we had? Remember, P had to be bigger than 0, right? P had to be bigger. So what if P is negative? Well, let's go back. Think about what that would be. Think about your series, the original series. We said, hey, what happens? Does this converge or diverge? If we have 1 over n to the p, right? We're like, when does this converge? When does this diverge? We went to the integral test. And our integral test gave us two really good conclusions. If p is bigger than 1, we've got convergence. If p is less than or equal to 1, we've got divergence. But this only worked if p was positive, right? What if p is negative? Come back over here. If p is negative, what? Imagine that's like negative. You bring it up, right? You bring it up. So like for example, if you had like 1 over n to the negative 2, right? That's p being negative, right? Bring it up. What is this? Sum n equals 1 to infinity of n squared. And what's that going to do? Do your nth term test. First test on the thing. What's the nth term test? Take the limit of that as it goes to infinity. What do you get? Infinity. Is that 0? Nope. Therefore, divergence. Okay? This thing should blow up, shouldn't it? I mean, you're basically squaring the number you're plugging in and adding it forever. It's going to blow up. So we have everything covered now. If our p is less than or equal to 1, we have divergence. Even if it goes negative, even if it goes into negatives, we still have divergence. And if p is positive, or sorry, is greater than 1, then we have convergence. All right? So p-series are very easy to do if you recognize them. So on a test or something, you would have to say, hey, look, this is a p-series. P is this number, greater than 1, therefore it converges. And that's it. You'd be done. What's that? There's a thing that they do, I think, with like tap shoes, and they put like sand, and they're like, yeah? It's like all sandy up here. I'm not sure. Can you hear it? It's just like someone threw a bunch of sand out here for me to.
I think you're just crazy. None of us can hear that.
Yeah. I am crazy, but you can hear it too.
We are now that close.
All right. Okay, everyone ready?
On the
Yes.
schedule real quick, this is categorized as power series, right?
Oh, where are we in the book?
On the schedule, like after exam 3, it says power series, but before that,
Oh, yeah, we're still way back. Hold on. We are in comparison test still. 8.3.
here's P series.
Yep. We are in 8.3 still.
Okay, very good.
Okay. Are y'all ready? Comparison test? Let me give you the general idea behind the comparison test, because a lot of students have trouble with this. Let's see if I can make it as simple as possible. So let's say that we have a series, all right? And I want to use the same notation that the formula sheet is going to use. So let's say we have some series, right? And we want to know if it converges or diverges, right? We've looked through n-term test. We tried, it's not geometric. P-series doesn't work. Integral test isn't something we feel like trying because it's too ugly looking. Maybe it has factorials in it. If it has factorials, we can't do an integral test. Do you all agree? Yeah. Okay, so we're sitting there, we're looking at it, we're like, I don't know what to do. But let's say we know this. There's some other series, and I'll do it in a different color. There's some other series over here. And that series is a series that we have up here, okay, in our heads. We know of a series that is somewhat, it's like they're almost the same. There's just maybe a slight difference in this one and this one. But this series right here, you know what it does, okay? So we know all we need to know about this one, all right? We know this one. And let's say what we know is that this one converges, right? Okay, so we have the series we want to know about. We have a series in our minds that we know converges that is somehow related to this series. Now, do you agree with this? If A sub n is less than or equal to B sub n, eventually, then this converges. Would that make sense? So what we're saying is this. I know that when I take all of these guys and add them up, When I add those up, it converges to a finite number, right? So this sum is finite. And I'm able to somehow demonstrate to you that these guys in here are always smaller than these guys, right? At the worst, they're the same. But these guys are always smaller or equal to those, right? And notice I put here not for all n. I put eventually. That means maybe in the beginning, these guys are bigger. Maybe the first three of these terms are bigger than the first three here. But after a certain point, these guys are always bigger than these guys. Then do you agree that that sum over there has to converge? Why? This is what you have to make sure you understand. Because it's smaller, right? I mean, if all of these guys add up to be a number, and all of these guys are always smaller than this, like for, you know, if I plug in a sub 1, it's smaller than or equal to a sub 2. I mean, sorry, b sub 1. So if they're, you know, each one compared side by side are smaller, then that sum has to be bigger than or equal to that sum. And if that converges, then that converges. Agree? Okay. Now, what if I do this a little different? What if I say that this one diverged? Then would this still be true? If this inequality is true, then that one would diverge? It wouldn't be true. So let's try and see if it makes sense. Imagine that this thing adds up and becomes divergent. It blows up, okay? And then you tell me that all of these guys are smaller than these guys. Then what can you tell me about that sum? It's smaller than infinity, which means that it could be infinity or it could converge. You still don't know. What could you do to change it so that it would be useful? Like if you know this one diverged and you know that this is flipped. What if this was flipped now? So what if I flip that? Now you know these guys are always bigger than these guys, right? This one's blowing up. Well, then that one has to blow up. Okay? Y'all getting it or not? Let's see if this makes sense here, reading it now off the page. Comparison test. It says here, see how it gives you two series, A sub n, B sub n on top of each other? I'll write it down the way it's written on the formula sheet. So what if it says this? It says here, first thing, it says if the sum B sub n converges and you have A sub n less than or equal to B sub n, then A sub n sum, that series converges. And then the second thing is if this series that you're comparing it to diverges and the inequality is the other way around, then the original series, the one you're interested in, diverges. Now, what does it say for the third one? There's a third here. I haven't mentioned this. Yeah, so this third one's really important. It's going to come up. It says, look, another thing you can do, if this inequality is something you don't want to mess with, there's another thing you can do. You can take the limit as n goes to infinity of A sub n over B sub n and see what you get as an answer. So it says if you get a limit, if this limit turns out to be a number, and it's very important here that you see this c has to be a number. It cannot be infinity. If you get infinity, this fails. So if you get a positive number, then both series converge or both diverge. That means if you take this limit and you get the number 2, then they both do the same thing. So remember, we knew about one of the series, right? We don't know anything about the other. So if you take the limit and get a nice number like this, like 2, then you know that they both either converge or they both either diverge. All right, we're going to have to run through some examples, all right? So let's do that now. Yes?
Is that kind of like, if I remember when it's like, let's say it was like A sub n minus B sub n. Something like to that extent where they both of them converge or diverge if they were subtracted or added.
Oh, okay, you're talking about the property of series, like if you have convergent series, you can add and subtract them. But if you have divergent, then you cannot assume that they add up to be divergent. So that is different because that's just how we algebraically can manipulate two series. This is talking about you're trying to figure out the convergence or divergence of this, and you're comparing it to a series that you've got up here, all right? Let's run through an example, right? You ready? Okay, let's do this one. So I'm going to say C or D, converge or diverge, right? That's what I'm asking. So sum n equals 1 to infinity of 1 over n squared plus 4. Okay, here we go. I'm a Cal 2 student, right? Trying to do well on this last exam. Asked if a series converges or diverges. First thing I'm going to do is I'm going to look at it, and I'm probably going to run the nth term test on it, right? So I run the nth term test, which means taking the limit of that as n goes to infinity. And I get 0, right? I get 0, which means nothing. Okay, so I move on. So then I look at it, and I'm like, is it geometric? Well, it's not geometric, right? It's not geometric. Because for geometric, you need to have like a number to a power. And the power needs to be the n. So that's not geometric. Okay? Is it a p-series? It looks like a p-series. But it's not a p-series because the p-series has to look like 1 over n to the p, right? This is 1 over n to the p plus 4. But it looks awfully like a p-series, right? Okay, there's a series that we haven't talked about yet. Is it harmonic? No, it's not harmonic, right? Harmonic is like a constant over a linear. Okay, it's not harmonic. Is it telescopic? Why is that not telescopic? Because if it was n squared minus 4, it would be telescopic. Because if it was n squared minus 4, then you would do like a partial fraction decomposition, right? If it was n minus 4, then I'd have to start it somewhere other than 1 because then we'd have an undefined piece. But I'm just saying, things to look for, right? It's not geometric. It's not harmonic. It's not a p-series. Integral test? We could do that with an integral test. We could. Because if I had to do an integral on that, it would be the integral from 1 to infinity of what? 1 over x squared plus 4, right? Could you integrate 1 over x squared plus 4? Sure, it's arctan, right? We could do an arctan on that. That integral would probably be pretty easy. Now, I would have to show that it's continuous, that it's positive, and that it's decreasing, so that might take me a little bit of time, right? So, I kind of, like you can see right now that, hopefully you can see, that the integral test would work here, and if you did that on an exam, that you would get the answer, okay? But there are other ways to do it, okay? And it's just, some are more efficient than others. I'm going to try comparison. All right? I'm going to try the comparison test. So this right here is our a sub n. I'm going to compare that to this. I'm going to let sum n equals 1 to infinity 1 over n squared be my comparison test, or be my comparison series. All right, so I'm comparing this series to this series. They are very similar, right? What can we say about that series? What type of series is this? This is a p-series, all right? It's a p-series, and what's p? P is 2, and 2 is greater than 1. And what happens to p-series when your p is bigger than 1? It does what? It converges. So, I have a convergent p-series that I'm going to compare to the series over there. And the reason I picked 1 over n squared is because it kind of looks like that, right? So now what is it that I need to show? I want to show what? I want to show that this thing is always smaller than or equal to the 1 over n squared. And that's because if this one converges, to say that one converges means this sum has to be smaller than this sum. So I want to show that 1 over n squared plus 4 is less than or equal to 1 over n squared. And this is pretty easy to show. I mean, look at the numerators are identical, right? The denominator on the left is bigger than the denominator on the right. So this fraction should be smaller than that one, yeah? Now, I am going to just do a little like cross multiplication. This is n squared less than or equal to n squared minus plus 4, right? And then just subtract n squared from both sides. If I subtract n squared from both sides, I get 0 is less than or equal to 4. Is that true? That's true. That's true always, isn't it? So that left side's always smaller than the right side, always. So this inequality holds. Therefore what? Final conclusion. Therefore, that sum, n equals 1 to infinity, of 1 over n squared plus 4 converges by the comparison test. Yes. Therefore. That's a pretty nice little test, right? It's a pretty nice test. I think that was more efficient than the integral test would have been. Do you agree? I think the integral test, we could have done it. It would have been a little bit of work.
I have a question.
Yes.
So we use the P series to get to comparison series. Is that right? Can you kind of explain just like the like a sum of the order of operations you just did?
Okay. I looked at this.
Yep.
I ran through a bunch of things. I knew I couldn't do a lot with it other than integral test.
Right.
But I recognized that if that 4 wasn't there, it would look like a P series.
Right.
So then I said, let me compare it to a P series that looks a lot like it. So I'm going to compare it to 1 over n squared. And then I know that converges. And because I know that converges, I have to show that this inequality is true.
Okay.
If I would have compared this, if I would have compared that to something over here that diverged, then I would have had to have shown this inequality flipped was true, which it would not have been true.
So if that diverges, then that would have been what?
This is flipped. Well, that has to be flipped and it has to be true.
Right.
Okay, let's do another one. Oh, you know what? While I've got this here, remember there was a part 3 on there that you can try? A part 3? So if I look at this part right here, this is the a sub n, right? And this right here is the b sub n that I'm comparing it to, right? Let's try that third thing. The third thing said, what I can do is I can do the limit as n goes to infinity of this one, a sub n, over that one, b sub n. Right? And if I do that, I can actually clean the fraction up first, right? This is like reciprocates and stuff. Limit n goes to infinity. I get n squared over n squared plus 4. Now I have infinity over infinity. L'Hopital a couple of times. And what would you get as your answer? You should get 1. You should get 1. And this says that if you do that limit and you get what? A constant c, which we did, right? Then what? They either both converge or they both diverge. So whatever they do, they both do. So I know what this one did, right? This one converged. So that means that one has to converge. Boy, that was even easier than having to do a comparison with the inequality, wasn't it? Just run the limit on it. So this would have got you the same conclusion running it this way. Yes?
So if you know that your comparison one converges and then you get some weird answer for the limit, do you know the other one diverges?
What do you mean a weird answer?
Like if it like goes to infinity
Okay.
or something.
Good question. So the question that's being asked is, let's say we took this limit and it went to infinity. And we know that this one converged. Are you saying from that can I conclude that that one diverged?
Yes.
No. This would be like the failed pregnancy test. This or defective. It's a defective test, okay? So the test would fail as soon as C is not a real number. Good question. Positive. Has to be positive, right? If you get 0, test fails. or negative. You won't ever get negative, only because these should be positive terms and these should be positive terms. Notice it says that on there. On the comparison, do you see on the far left underneath the two sums, it says a sub n greater than 0, b sub n greater than 0. So this test is not going to work when it comes to an alternating series. We'll have a different test though. Okay? So we should always get a positive number unless we get 0 or infinity. If we get 0 or infinity, test is over. Got to try something else. Okay? Let's do... Okay, I like this one. Sum n equals 1 to infinity of k squared minus 1, or n squared minus 1, sorry, over 3 n to the 4th plus 1. All right, here we go. I'm a Cal 2 student. I want to do well on the final. First thing I'm going to do is I'm going to take probably the limit of that as n goes to infinity. And I'm going to realize that after a couple of applications of L'Hopital's rule, I'm going to get 0. And that means it's going to fail, right? That test fails, and I move on. It's not geometric. It's not telescopic because I can't factor the denominator. It's not a p-series. It's not harmonic. Boy, I wish it were harmonic. It is integral test. Anybody feel like integrating that? I don't think I want to integrate that. Which means we don't have a whole lot left other than comparison test, right? So if we're going to compare it, what are we going to compare it to? N squared over, wait, what did you say? N squared over what? N to the 4th? So like 1 over n squared? So your idea is that if n gets huge, right? If n gets huge, this numerator is really kind of just acting like n squared. And the denominator is pretty much acting like n to the 4th. Like adding 1 doesn't make a difference. Multiplying by 3 doesn't necessarily make that big of a difference. This looks a lot like it would be just like an n squared over n to the 4th, right? Which means maybe 1 over n squared would be something to compare it to. Let's try it. That worth a shot? Let's do it. We're going to compare it. Let's compare it to the series sum n equals 1 to infinity of 1 over n squared and see what happens. Now we know about this series, right? What does the series do? It converges. This is a p series. It converges because p is 2, which is bigger than 1. Okay, so we are comparing to a convergent p-series. So now we have two options. We can either mess with the inequalities or we can do the limit. What do you all want to do? You want to try the limit first? Just see what happens. It might go fast with the limit. You want to try it? Yeah? Yes?
So they both are going to work?
No, they may not both work.
Oh, okay.
That's right. They may not both work. Yeah. Okay, so y'all want to start with the limit first. So let's do the limit. Let's do the limit as n goes to infinity of n squared minus 1 over 3n to the 4th plus 1 over 1 over n squared. Bam, I think this is going to work. Because this is going to become limit n goes to infinity. Let's see, this n squared comes up top and hits this and this. It becomes n to the 4th minus 1 over 3n to the 4th plus 1. Minus n squared, sorry, n squared. Distribute that n squared through. And now you have infinity over infinity. A couple of applications of L'Hopital's rule. You should get 1/3 here, which is a number, right? This is a positive constant, which is required. So whatever one does, they both do. Go ahead.
In the original, so in the original one, it's n squared minus 1. Why couldn't that looks a lot similar to what we have here. Why couldn't we also do L'Hopital's from the beginning if that's also indeterminate?
This right here?
Yeah.
Oh, we did. The very first thing we ever did on this was let n go to infinity.
Right. So
And we got 0, which is the nth term test, which is the first test. And anytime we get 0, that tells us nothing.
okay. Fair enough.
Right?
Yep.
Okay. Okay. That was nice. That worked out real nice. Now I don't want you to fall in love with the limit because it doesn't always work, okay? Let me see if I can't give you one that doesn't work. No. Okay, how about this one? All right. First thing you always do is the nth term test, right? Nth term test, you're going to get 0, so you're going to move on. It's not geometric. It's not harmonic. It's not telescopic because it doesn't factor out. It's not a p-series. If the +1 wasn't there, it'd be a p-series, right? If the +1 wasn't there, that would be n to a power on the bottom. So how about a comparison series? What do you think? We have to come up with something to compare it with, though. Okay, so let's compare it to sum n equals 1 to infinity of 1 over what? Square root of n cubed, which is really a p-series, which is going to be n to the 3 halves. So p is 3 halves, which is bigger than 1, so this converges. Right? That converges. Okay. So you want to do limit? Man, this limit comparison is just a monster, isn't it? This thing is awesome. Because I'm going to do limit, n goes to infinity of that one over this one. And then you do your reciprocal again, right? And when you do them and you do the reciprocal, I can do this. Right? Because you have the same root on top and bottom. So if you have the same root on top and bottom, you can just put them together. And now this limit's going to be very straightforward because you go take the limit inside and you just L'Hopital, L'Hopital, L'Hopital. And you get root 1, which is 1, positive constant. Boom. So whatever 1 does, they both do. Man, this thing is impressive. I need to get one that's not going to work. Hold on. I thought I had one in my notes. Well, normally, here's the thing. Normally in my notes, I don't give you the limit comparison until after I've done just comparison. So let me find one here. I just need to look at one to make sure it's going to do what I want it to do. Are we 8.3?